Hello, we're recording. All right, so there's been a bunch of questions on the test. The first question is, what is my grade? So your grade is what is on the third page of the test. That's your actual grade. So it's not out of 100, and I think it was 120 points, but maybe it was 125. But that's what your score is. It's based out of 100. So I did this with my other class, and I like to do it this way too. It's just a personal preference thing. I don't like to scale anything because when you scale things, that seems cheap. People are giving you things. I like people to earn their points. So you earned those points. Make sense? So it's a way for you to get higher than 100 points. But if you doink a problem or two, it's not gonna mean the result that you're getting a failing grade or something like that. Okay. Any questions on understanding your grade? You can double check in Brightspace too. That's what it's entered in, and it should show you there because Brightspace is the official log of how we'll do things. Okay. Share my screen. Do you want to go over the test or not really?
Could we go over a few problems?
Well, my perspective is we just do the whole thing or none, unless there's a real challenging part.
No, I mean, it wasn't really challenging, but I wasn't, for some reason, I was so confused. It could be really easy problem, but I was so confused.
Well, let's do them all really quickly, but I'm not going to give you answers. I'll just tell you how I do the problems. That's okay with people in TV land?
Yeah, that'd be helpful. Sure.
Yes, that's fine.
Right, because perhaps you had an issue with number 2, somebody might have had issue with number 1. It's just by the time you ask what issues you had, you might as well just do the whole test. So, all right, so number 1, again, I'm not going to give you the answer, but you were told you had electricity rates of 18 cents per kilowatt hour or $0.18 per kilowatt hour. You needed to figure out what the dollars were per year, right? Because that's what it says. What would it cost to run a 75-watt bulb for an entire year? So that's dollars per year, correct? It's not dollars, it's dollars over the course of a year. So if I multiply this by 0.075 kW, because that's the rating of the light bulb in kilowatts, I can cancel out my kilowatts here. Now I'm in dollars per hour. I need dollars per year. So I multiply by 24 hours in a day. And then that's going to be allowing me to cancel out my hours, but now I have dollars per day. I need dollars per year. So then I multiply 365 days per year. And then I'm only left with the units of dollars per hour or dollars per year, not dollars per hour. You can do cents or dollars. It doesn't matter. It's the same thing, right? You just divide by 100 or multiply by 100. Say that again.
I heard 75 watt for a while.
Okay.
You when you start with like the more
I agree. I think if you actually just start out by saying, what are my units that I want? I've got dollars per year. Then you can kind of start to see how it's literally just a unit conversion. And that's a good way to check your result. In MathCAD, we don't really use MathCAD all that much, but there's an auto feature for doing unit checks, all automatically done for you. So it's pretty good. So if you're really struggling with a problem or a test or something like that, bring it down to the basic units and see if you can come up with an answer that way. A lot of times it'll save you because if you're expecting a result to be volts, but you get ohms, you've made a mistake, right? So it's a good way to check. All right, number 2, I'll give you a really good hint to start this one. Plus minus 100 volts. This is a 20 ohm resistor. The current through here is 2 amps. Then I have a 3 amp current source, 4 ohms, plus to minus 25 volts. And it was asking for what is the resistor of R to make this work. And then what is V out? So find R and V out to get the circuit. Well, the first thing you do is try to look at information that you can pretty quickly solve for. The very first thing I can do is I can solve for the fact that I've got a 40-volt voltage drop across there because it's 20 amps, 2 amps going through a 20 ohm resistor. Which means from Kirchhoff's voltage law that this has to be plus to minus 60 volts across there, correct? Minus to plus to minus is dropping in that direction. The next thing I have is I've got 2 amps going into this node and 3 amps going into this node. So now I must have 5 amps going in that direction, which means I should be able to calculate that voltage drop pretty easily. Now I know this voltage here. I know the voltage drop here. I know this voltage. The only voltage I don't know is V out. So you can use KVL to solve for V out. Once you have V out, you know that this has to be 5 amps. You should be able to solve for R. Okay.
Yeah, I mean, I was confused if that 2 amps is the actual 2 amps going through the resistor, because I was so confused and I kind of overthought a lot. Like if I have to consider all other elements, like current flowing, so I think the data is different.
So you did have to include all the elements because that was the reason why it determined 2 amps, but that resistor value R is what you needed to select to get 200 amps out of the 100-volt power supply. Okay, that was the only thing that really, if you didn't have that, you'd never be able to solve for R, I think. Okay. Any questions on number 2? Because there were some problems with 7, 8, 9, and 10, but I think in terms of the circuit analysis one, people had the most problem with this one, number 2. Do you see why it's supposed to be negative? Okay. Okay, yeah, if you get 140 volts, your answers get a little screwy. But if you just do KVL, if you're ever stuck, I always make the recommendation, just say, I've got plus to minus 100. I've got plus to minus 40, and then I can just show this as an open voltage here, because this is just what the voltages need to be. And then V, we'll call it not V out, but V, we'll call it VA, plus to minus in this direction. So just do KVL, minus 100 plus 40 plus VA has to equal 0. So VA equals positive 60. If you just do it that way, it takes, the guesswork out of it. Is it adding or subtracting? But you got to maintain those plus minuses. That's the other part of it. Okay. Any other discussion on number 2? Yes, sir.
So I always had this problem of when I assume where this current is flowing from where to where. I was so confused because they're all like 2 amps is going in and 3 amps is going in, and there's only one way to current to flow out, which is towards the plus of the 25 volts. And I was so confused because that doesn't really make sense to me. So
Why does it not make sense?
maybe I was just so unfamiliar with like having the current flow towards the plus.
So having the voltage, the current flow into the positive. Well, remember what an ideal power source is. An ideal power source is one that does everything it needs to maintain the voltage that you specify. So in this case, it is absorbing power. Remember we talked about dissipating power and absorbing power. This power source is not providing power. It is absorbing or dissipating power.
Oh.
So it's supply or dissipate, just like in your car battery, right? Did you get in your car this morning and start it up? Walk, okay, but if you drove a car in the last week, maybe turn the key. Why doesn't that battery go to 0 after a couple of maybe 20 starts? Because at some point it's taking power out, and most of the time it's bringing power in from the alternator. So it's bidirectional. It better. So the question is, does the car run off the alternator when it's running? And the answer is it better, because if you need your battery to support your alternator, to go for a long drive, at some point your car is going to shut down. So your battery should never be needed to maintain the current flow. Now, if you're somebody who, you know, modifies your cars and put in crazy radios and stuff like that, that consume gobs and gobs of power, that's different. But all car manufacturers, they size their alternator for maintaining all the load of the vehicle. And if you look at some of the towing vehicles, like pickup trucks, for example, you can get an oversized alternator. Anybody know why? You just have a lot of auxiliaries. So you might have to provide power to the batteries, the lights on whatever you're pulling. You might want to put something, plug it into the cigarette lighter and have additional lights. So it just gives you that extra capacity so that you can tow whatever you need to without having to do that. So that would be a heavy duty battery or heavy duty charger. But you still don't need to upsize the battery. As long as the battery is able to start the vehicle over the next 6 years, then that's all you need. Partly the cold cranking amps, it's a little more than that, but that's like the general capacity of a battery to be able to start something, because you need a lot of power. Your starter is the one that absorbs the most amount of power. So when you hit your starter, it pulls in massive amounts of current. And if you can't pull in a massive amount of current, it might not have enough oomph to turn it over. But there's also an amp hour rating on the battery, which is, okay, what if you're going to park your car for an hour or two and you're going to listen to music or something like that? You know, that's a factor as well. And then also batteries degrade pretty rapidly. So a friend of mine, we bought a car off them, and it was a plug-in hybrid car. And I bought it from him last year, and it was a 9-year-old battery. And he's like, I don't know why the car won't stay charged. It's a hybrid. There's a 350 volt battery in the back. It's like, sure, but over time, the electrolytes in those batteries decay. So even if you sat it all day on a charger, the moment you take off the charger, it just doesn't have any internal capacity to do it. So you should plan on having that replaced. So most car manufacturers will say, replace your battery 5 or 6 years. Tesla, because the same print has a Tesla, and they have a small battery, they would have to replace every 4 years at like $500. So it's very different. So even a Tesla with this massive battery pack still has a 12 volt battery on it. So, and it won't run if the 12 volt battery doesn't hold charge. So figure that one out. You've got this 100 kilowatt hour battery, and this little tiny 12 volt battery. If that doesn't work, your car doesn't run. So kind of goofy. All right, any questions? You can also add capacity. Marine deep cycle batteries have different characteristics. And now you're starting to buy car batteries. They're lithium type batteries, or they're gel type batteries, which have more capacity. They're very expensive. Still, lead acid batteries are so much cheaper. That's why they dominate. And recycling on lead acid is really good. So that's one of the big things you're hearing about EV vehicles is, what is the future of EV? We're going to dump all this lithium. At some point, they'll figure out a way to recycle it, because there'll be enough capacity and there'll be enough incentivizing to go ahead and say, yep, we need to go ahead and redo this. So there'd be a core charge. Like right now, if you go buy a battery at, I don't know, Walmart, let's say, you have to pay an additional $10 or $20. I don't know what it is when you buy that battery. And that's just basically like when you go buy a soda at the store, you put a 5 cents returnable, you get that money back when you return the can. So that incentivizes you to bring the can back. But 5 cents for people today is not incentive enough. But if it's 10 or 20 bucks, you take your old battery, I'll say, yeah, I'm going to go get my $10 or $20 back and do it that way. So maybe car batteries that are like that, maybe they'll have a $500 refundable, something that makes it worth your while. All right, number 3. Sorry for the education. I like this stuff because this is all relevant to the power industry, but I also teach a course on renewable energies with David Dvorak. And so we get into a lot of these different topics about, you know, the environment and renewables and waste and all that stuff. So this one was a little bit of a struggle as well. And I was hoping this was going to be a fairly quick and dirty problem. So some people forgot the fact that this was 2 VR. So they just put whatever the voltage was there, the voltage drop across here, and just put it in there. It's 2 times VR, okay? So you know the current through here is 3 amps. You directly know what the voltage drop is or what VR is equal to. So solving for 2VR should be pretty easy. And then it said, find V out, which is, in this case, this is V out across here. It's just KVL. I know the voltage drop here. I know the voltage drop here. It should be pretty easy to do that. And then the only other thing is the power in the dependent source and the power delivered to the load. Well, once you have the voltage drop here, should be able to calculate power here, and you already know what this voltage is. You know the current, so you should be able to calculate what the dissipated power is in the dependent source. This one I was hoping was going to be a really simple problem. Any questions on number 3? Okay, number 4. So we had a series circuit. It's 2 ohms, 6 volts. Then we have a current source that is 2 amps. This voltage is plus to minus VO. 5 ohms. And 4 ohms. And this was 12 volts. So what I was hoping you would see when you do these problems is you see it's a series circuit, right? So it's a series circuit, which might tell you, hey, let's write loop equations. But if you notice, the current in here is already told for you. So this loop current, you know, has to be equal to 2 amps because that ideal current source forces it to be 2 amps. Okay. So you knew what IR1 was. This is R1 because there was a current source dictating what that current needed to be. And then it said find V out. Well, V out is over here. All you had to do is go ahead and open circuit that, and then just include the fact that you have 2 volts or 2 amps, which is going to cause plus to minus voltage drops in that direction. And then there's just a KVL loop. That was it for number 4. Questions on that? Am I going too fast? Is this, or is this so easy that you don't have questions?
So what do you have an ideal current source that we taking the whole circuit that's the current for the
That's the concept, right, of a current source, that if it's in whatever's in series with that element, it has to see that current because the current source is going to do what it takes, mean generate whatever voltage it needs to drive 2 amps. Like you could not add a current source for 1 amp in this direction and expect that circuit to work because one current source would say go 1 amp this way. The other one says go 2 amps the other direction. It's not going to fly. So with current sources, you have to be very careful because they are forcing electrons in that direction. Okay, this is ideal. In the real world, something would change. Whatever the more powerful power supply would be, eventually would say, I'm putting 2 amps in here, and this one would probably burn up, or the other way around. We don't know which is the more powerful of the two. But that's the concept. Now, if you put them in parallel, no problem. As long as you have some place for that current to go, you can certainly put different currents sources in parallel. It's the same thing for voltages. I can't have a 12-volt system and put across it in parallel a 5-volt. One of the two is not going to be happy with that situation. Probably both are going to fight each other. So current sources in parallel are okay, but not in series. Voltage sources in series are okay, but not in parallel. Okay. Now, I say that with a caveat because in the real world, the whole world is in parallel. We always put stuff in parallel. There are 3 generators just down the road at Main Independence Station. They are all connected at a common bus. They're all voltage sources essentially. But here's the thing. This here is monitoring the voltage and the current out of the bus. And it is adjusting the voltage and the current continuously so that it doesn't fight. That's something we'll talk about more next semester when we look at control systems. So you're actually, so if you wanted to put these two in parallel with each other, what you would do is say, okay, well, I'm going to set this to 12 volts, but I'm going to make this an adjustable supply so that once I get to a certain value of power output, then I'm going to start to back off my voltage because I don't want to damage the unit. So when you actually operate in parallel, things are a little bit different. And so why am I bringing this up? Because everybody heard the term of a microgrid, perhaps? Like campus could be a microgrid where we could separate temporarily from Bangor Hydro completely, and we get some generators around here that we could perhaps, if the things are set up correctly, we could run our own grid. The problem with that is that this generator right outside our door, our window here, might be fighting with the generator that's over at Neville because they would want to maintain slightly different voltages. So what happens is one has to sort of pick, I'm going to set this voltage and this frequency because in AC it's frequency. And then all the other generators have to adjust their output. I'm going to pick up the slack. So my voltage will never change. So I'll either do something for my speed or something for my power input to make that work. All the other generators have to sort of adjust themselves based on what that call is. And so that's what's happening at the grid level. Usually you have very large generators like nuclear power plants that are so much bigger than anybody else that they can really control the frequency. In Millstone, Unit 3, they have a 1500 MVA generator that there's no other generator in New England that's that big. So if I have a generator down the street, if it's 200 MVA and it does everything it can't force Millstone to move off its voltage. So that's why really big generators usually are really good as long as it's well maintained and owned and operated. Those set the voltage and frequency, and then everybody else sort of has to adjust themselves to that. And people have known this for years, but we just deal with it. So that's why if you're at your house and you've got a portable generator and you're saying, hey, I want to get more power, so I put two, you can't just connect them to each other because they'll fight each other. No, eventually will cause issues. So the portable generators is the case where you better not add another generator in and connect it into your system, or else you get some issues there. All right, enough blabbering, right? Let's get to business. So let's see, 4 amps, 24 ohms, 12, another current source. This is 10. And this is 8. So it asks you to solve for V, the plus to minus voltage V. And then it asks to solve for IR1, which is the current through the 24 ohm resistor. You have a bunch of elements here, but they're all connected in parallel with each other. So wouldn't it make sense to do nodal analysis on this problem? So all you got to do is nodal analysis. If you want, you could redraw the circuit and combine the 4 and the 10, make it a 6 if you want, but you don't need to. That's it. Now, one thing that made me a little concerned, there are a number of people who said this is VA and this is VB. And then they had matrices that were 2x2 matrices. You can't do that. These are the same voltage. How can they be different? It's a common connection between the two. So when you start assigning different voltages and trying to do those calculations, you're heading down a dangerous path. This is all a common node. And so if you remember, I said, go ahead and just highlight what the nodes are. This is one node. And this is the other node. The other ones, there's no other node. They're all connected to the same points. So I have 2 nodes, but 1 to solve, because this is my reference. Any questions on that? So far, so good? Any of these sneaky so far? I wasn't trying to be sneaky. This was just, hopefully this is the stuff up to this point, and even the next problem, number 6, and also number 7, that if I had given you this test at the beginning of the semester, you could have done 1 through 7 pretty well. Is that a reasonable statement? Not too well. You don't have to do matrices. Pardon me?
Until we went over them, I would have probably done that.
Because you had forgotten from 112, 111 or whatever. That's fine. That's why we have this class, right? It's get everybody back up to speed so that, now you've seen it once, maybe twice. And this is perhaps the third time you're seeing it. So now it's really starting to sink in saying, oh, it's just this. So. Okay. Number 6, which is a bunch of loop equations. Do I even need to write this one down, or do people feel pretty comfortable with this one? It's just a lot to write down. That's why I don't know if I need to. Most people got this one right. Yeah, people put stuff in the wrong spot in the matrices, and as long as you had the general approach correct, I was fine. Giving you most of the credit. So number 6 was probably just rudimentary, go back to 111, plug and chug. So unless anybody wants to see it, I won't do that now. Number 7 is a dependent source. Again, it is a common node. So this is 7. This is 6. People may have got confused because this is V over 4, but the arrow right inside there dictates that this is a current source. Just because the controlling variable is a voltage source, that doesn't mean that it is a voltage, okay? It is a current source if you see as an arrow. It is a voltage source if you see plus and minus. That's the key sort of thing to understand. Don't get caught up into what is, the controlling variable for the dependent source. You're going to give yourself a lot of agina. Oh, here's 3 ohms and 2 amps. Find the voltage across those two. So perfect opportunity to do KVL, right? Or not KVL, KCL. You have a common node. You only have current sources. You don't have to do anything with super nodes or anything like that. So let's do it. We only have one node, and I'll do the highlight again that we need to solve for the voltage. There are 2 nodes, but only one that we need to solve for. So we're going to solve for the yellow node voltage, which means write your KVL equation. The hard part was this V over 4, right? And the voltage, the driving voltage was over here. So all you need to do to handle that is, this is the current in, and I'm going to assume the rest are currents out, equals V over 6 plus V over 3 and plus 2. You only had to write one equation. You don't actually have to write 2 equations because the voltage that you need to solve for just falls out of this. So normally, and this is the very rare exception, when you have dependent sources, you have to write at least an additional equation to solve for that dependent term or dependent parameter. You didn't need to do that here. Pardon? That's okay. You could, but all you know is that V1 equals V. Well, what's the confusion? Okay. Yeah, so, and it's a really good point. So the focus is understanding what are you looking at. So if you're looking at plus to minus V and you're not exactly sure what it is, go ahead and put a multimeter, draw a little multimeter and say, here's my plus terminal, here's my minus terminal. What voltage am I measuring? So bring your probes away from just looking at that current source, and bring your probes all the way to the end of where, another node or another impedance device comes into effect. And then sometimes it reveals that's just the same voltage. I don't need to solve for that. This one was also another one where a few people did VA and VB. And I would just caution you, because that you got to go back to the fundamental understanding of what a voltage is, right? A voltage is a potential difference. What is the potential difference if I measured in my voltmeter, what's the potential difference between VA and VB? It has to be 0 because you're looking across an impedance of 0. So no matter what current you have through there, it could be millions and millions of amps. Millions and millions of amps times 0 is still 0. So the potential difference VA to B, which is the plus minus, has to be 0, which means VA has to be equal to VB. Because VAB, by definition, is VA minus VB. All right. So if you're not seeing that, at least from a circuit layout perspective, my suggestion is to go back in and take a look and see, okay, do I actually have a voltage there? And then just go ahead and use, the multimeter. Sometimes it just really helps. It just changes your perception. If you can't see it by looking at it and very quickly, try pretending you get a multimeter and you're going to throw it in. As long as you're reasonably comfortable as a multimeter, most of us are really comfortable with voltages, currents. Some people forget you have to open the circuit and put that in series with it. Although you almost don't even need to do that now. Everybody know how you measure current now?
Yeah, with the clamp.
That's how you used to do it. What's that? You do a clamp on.
Yep.
Yeah, so if you have, clamp-ons, you actually work for DC. It used to be only for AC, but now they have what are called Hall effect type ones. Because what you're doing is whenever you have a current, and we'll learn more about this if you take 321 with me, whenever you have a current carrying wire, you have magnetic fields that emanate outside of that. So if I can put another device that can loop around and see that magnetic field, that's going to induce a current, and then I can measure a voltage there. But that only works if the current is change or the flux is changing, which means the current has to change. So with DC over time, this is just going to reach steady state, and that current will be equal to 0. But if you take a look at Hall effect, it works on a very different principle. So now you can get clamp-on meters that will work very well for AC and DC. And so you can go buy a Fluke clamp-on for, I think it's $80. What is it? The Fluke? Does anybody know what a Fluke clamp-on meter is? Costs? $300 for the clamp-ons?
I know that the DC clamp-ons are more expensive.
Let me see. Clamp-on.
Some of them I use can get pretty expensive though.
Yeah, it's Fluke after all.
Yeah.
$150, so I was off by a little bit, but that's still pretty cheap. Now somebody's gonna say, hey, Paul, you're BSing me. What if this only goes down to a range of 200? You can only measure 200 amps. How can you get more accurate? You take your wire and wrap it around inside your clamp a couple of times if you can. And each wrap multiplies. So when you have 2 wraps in there, it doubles the current. 3 triples, 4, 5, 6. So one of the tricks that you can use if you don't have a clamp on that goes down to the light accuracy, if you can wrap your wire around a couple times inside that clamp, and then you can get a much better, more accurate reading. You just have to divide by the number of turns. It's basically what you've done when you wrap the wire around, you built a transformer. It's essentially all you've done. So it's not $400, but I don't know if this is a good price for this one. $150 it seems reasonable. Not a college student. How much did you pay for your cell phone, Ethan?
Nothing.
Nothing? How much a month do you pay for a cell phone? Yeah, folks help you out maybe? Which, well, but that still costs you money, right? So I always tell people it's everybody complains about their electricity bill. I pay $120 a month. Oh my God, the world's coming to an end. Then you ask a question, how much you pay for your cell phone? $340? You're paying almost triple what you're paying for your electricity. Do you have any issue with it? Well, but my cell phone gives me all this technology and I can see all these things. Yeah, but would your cell phone really do all those things if you didn't have electricity? How would you eat? How would you wash your clothes? So it's just a commodity that we take for granted, like water. You turn on your faucet and there's water there. What if it doesn't come out? And we laugh, but look at what's happening in Florida right now. Now they have to boil water. They don't have electricity. You drink too much water? They have too much water, but it's not potable. That's the issue. So there's a lot of things to think about and what's going on in Ukraine. There's a lot of different 4 to 20 milliamp test clamp ammeter.
Yeah, that's one I've used before, and it's like $900. So
Well, Jordan likes caviar. He doesn't eat, he's
no,
not
not
eating
me.
mac and cheese.
PCA likes it.
Ah, fair enough.
Yeah.
Yeah, so, that's the thing, when a company pays for it, all bets are off, but for a college student, you can even make your own if you really got clever with it.
Yeah, mine's like $5.
You have a $500 one?
No, $5.
Oh, $5. Okay.
Yeah.
The built ones get a little bit.
The hand-built ones?
Yeah, built, analog and digital one. The analog one. Fit on the digital.
Is that because of operator error in constructing it?
The parts, like, some of the parts aren't exact, so. Stuff doesn't become.
Yeah, so you're talking about the manufacturing quality is like, because they're trying to make kits as cheap as possible to get people. And for the most part, as long as you have a ballpark number, that's probably fine. I mean, within 10% usually is okay. Most of the time when you're out in industry, and again, I can only talk about my own experience, but unless you're doing really detailed calculations where you're really checking, okay, is something too hot and burning a product like a PCA, for example, so an amp makes a difference. But in the power industry, if it's off by 30, 40 amps, that's noise. I mean, you just don't even think about it. It doesn't even matter to you. So like your house, when was the last time anybody changed the meter at your apartment at your house? It might be 20 years old. That's not calibrated anymore, but you still pay your electricity bill. So. All right, number 8. This is one I was surprised people struggled with. I'll give you a hint how to get started. Remember how we talked about doing tables? You don't have to graph it. I just said find IFT, PAT, and work of time. I never said draw the graphs. Some people did, which is fine, but my suggestion is just go ahead and set up the times. The time we see from 0 to 4, it's a fixed constant slope. From 4 to 8, it's fixed. From 8 to 10, it's fixed, and anything beyond 10, it's 0, right? So the first thing it says is, all right, we have a 0.2 farad capacitor, and we're given the voltage here. So we know that VC of t equals C di dt, right? So if we want to solve for I of t, wait a minute, let me fix my equation here. I have this backwards. IC of t equals 1 over C. No, C dV dt. Why am I doing this backwards? dV dt. So at this point, all I need to do is find the derivative of the voltage, which I'm given. Those are the plots. And then I multiply that by my capacitance and I'll get I. So I'll start off, I'll give you the first ones from 0 to 4, dV dt is equal to the change in Y over the change in X. It changes positive 80 divided by 4 seconds. So that has a dV dt of 20. A lot of people miss this next one from 4 to 8. It's 0. There is no slope. From 8 to 10, it's a negative number because it started at 80 and then it went down to 0. So it's minus 80 divided by 2, minus 40. And anything greater than 10, it's 0. There's no data. So at this point, you should be able to do IC equals C dV dt, knowing that the capacitor is 0.2 farad. Okay. Once you have that, now we want to go ahead and usually just do our power. So you take the power. So at the beginning of time, it's 0. And the voltage is going to be 0 as well. So you take your voltage is 0. So you know your power starts off at 0. Then eventually the voltage goes to 80. And my current is going to be a fixed value here. So it's going to go to 80 times I. Power can change instantaneously in a capacitor. So I don't copy this into the next one. That's not required here. Okay. Let me just go ahead and put the 4, so C times that, this should be equal to 4 amps. So this is, we'll put 320. And then the next one, the power is 0. Why is that? Because there's no current. There's no current, there's no power, which makes sense because we're no longer charging the capacitor. So we're not putting in any power or taking out any power. It is a fixed flat value. Okay. So you should be able to finish that. Now to do the work, because this goes from 0 up to 320 and it looks like a triangle. And so this might be worthwhile to actually draw this as a graph because you can actually see it better. Where when you do the power, you just multiply it, but to get the work, what you see is you start out at 0 and then you eventually work out to 1/2 the base times the height. The base is 4, the height is 320, 1/2 the base, 1/2 of 4 is 2, times the height, which is 320. Eventually, it works its way up to 640 joules. And in work, your joules can't just instantaneously change. So that moves on to your next value here. Okay, and it stays at 640 because you're neither charging or just charging. So that becomes the next one over here. And on and on and on and on. Questions on this? A lot of rolling heads. Let me see in TV land. Any rolling heads saying, oh boy?
What was the equation you used for power?
Power is instantaneous power. It's just equal to V of t times I of t. So everywhere in time, you take that voltage and you multiply it by that current and you get power. Okay. Any other questions or comments from TV land?
Very good. I had the same question for power, but I think I get it.
Yeah, so it's a really good point. I can't remember who asked it, but perhaps it was Sean. But the equation for power of time, this is called instantaneous power. Okay, and we'll see that when we start looking at AC circuit analysis. For those of you in 312, for example, the power that you're calculating in AC circuits is not an instantaneous power. It's an average power. But it's, if you actually look at what power calculation is, it's really take any instant in time, find the voltage and multiply it by that same instant in time current. That's how you get the power at that instant in time. What we do when we talk about AC circuits, that's why we talk about a 100 horsepower motor, because that's what the machine is capable of doing. That's what it's capable of outputting for mechanical power, is the equivalent of 100 horsepower. But that doesn't actually mean that that's actually what it's putting out. It puts out whatever it needs to. And when we start talking about capacitors and inductors that have the ability to store energy in magnetic fields, well, that energy stored has to go back at some point because it's not doing anything with it. So unless you just keep the capacitor charged forever, you have to send it back. So in AC systems, at some point your capacitors are being charged, and at some point they're being discharged. And so how you take that into account with average power is you come up with a term called reactive power or imaginary power. John might, when you get exposed to it in 312, he might talk about that. And I know Jude likes to use the concept of it's the foam for the beer, but it actually is not. It's actually real power. So it's real beer that's doing something that's necessary. It's just not doing anything useful. Eventually the foam will go back to beer if you don't throw it on the counter or something like that and just let it go away. But it's going to go back to that power. This is power that actually gets sent back to the generator, and then the generators have to deal with it. They have to be able to absorb that power. Okay. So that's instantaneous power versus average power. Any other questions on number 8? Okay. Number 9 was you had a graph. And I said, find V of t. So you have an inductor. So VL of t equals L di dt. Start with our base equation. We have a derivative. So we're gonna do our time intervals again, and I just like it this way because it makes it very, when you do a graph, sometimes it's harder to see the information, but if you have numbers, people seem to find it a little bit easier to use numbers. So my time intervals, I have a fixed slope from 0 to 2. No change in the slope from 2 to 4. And from 4 to 10, I have a fixed value, and then greater than 10, there's no change. So the first thing I'm going to do is take the derivative of I with respect to time, di dt. So the slope, and got to be careful here of the units, it rises 30 milliamps in 2 microseconds. So the slope is 30 milli over 2 micro, which is, got to be careful. This is 10 to the minus 3, but this is 10 to the minus 6. So that becomes 2.5 K, right? Is the slope there? 1.5? Yeah, 1.5, not 2.5. Sorry about that. 1.5 K.
Oh, actually, it's 15K.
15K, yes. The easiest way to do it, let's just keep expanding it here. So let's erase this. And let's do 30 times 10 to the minus 3 over 2 times 10 to the minus 6. When you divide exponentials, you subtract them, correct? So this becomes 30 over 2 times 10 to the minus 3 because I subtract them. When I invert 10 to the minus 3, it becomes 10 to the positive 3, because 1 over 10 to the minus 3 is 10 to the positive 3. So that's equal to 15 times 10 to the third. So if you just keep track of your exponents, it should fall right out for you. Okay. 2 to 4, it's 0. 4 to 10, it's going to be, let's see, we have minus 30 because we started at 30. And then we go in 6 microseconds. So that should be equal to, so it's 30 divided by 6. So that should be minus 5. Okay. And then anything greater than that is equal to 0. To solve for that, and sorry, this gets a little crazy because I showed all the work. VC equals, or VL, sorry, equals L di dt. Just multiply those values by L. And that was it. Questions on number 9. Okay, number 10 was a thinking one. And I'm trying to get you to think because it might be a setup depending how the rest of the semester goes in covering material. We're getting a square tooth wave and we want to get a sawtooth. So square to sawtooth. Which one do you think is harder to replicate in the real world? Something that does this sort of instantaneously or something that does this? Which one would be easier to make?
Square.
The square is easier to make? The sawtooth? In reality, to build something like this, it's not possible. What would actually look like here is you would have, if I can zoom in a little bit, you would have something that does this and kind of slopes off that way. So to get these really sharp corners, you have to do a lot of work to make that happen. Over here, it's a big change because it's going up in slope and then it goes down in slope, but at least it's not an instantaneous change. So it's maybe a little bit more permissible. So if we have time this semester, we'll do something called a Fourier series. And the way that we'll cover Fourier series is you just keep adding a bunch of frequencies if it's periodic. If it's non-periodic, you have to add all the frequencies, but you're adding these integral multiples of frequencies. And the more you add, the more you can get to these really sharp edges, those sharp corners. Over here, you don't have those sharp corners. So this is going to take less frequencies, higher and higher values to get there. So what I'm building essentially is a filter, a low pass filter. So I'm taking a current. Here's my current going in. And I'm running it through a low pass filter and getting a voltage out. So your question is, how do you go ahead and convert that current to a voltage? Well, you've got a bunch of different options. You've got a resistor, an inductor, or a capacitor to do it. A resistor just takes the input and divides by that value. So whatever the current is, you multiply by the resistance and you get the value. So the shape is going to be the same. So that's not going to work so well. Let's take a look at an inductor. So L, we're going to use LdIdt. So if we take the derivative of this square, what is the derivative of that? 0 and 0 eventually. So what we would have is we would have something that looks like this. It's 0, spikes up crazy high, and then goes back to 0. So if we put an inductor there, is our output voltage, does our output voltage, which is a sawtooth, look like this? Not even close, right? So probably can't be a capacitor, an inductor. Let's look at a capacitor. VC is equal to the integral 1 over C. So the integral, what can we make this work? Well, we see that we do not have an instantaneous change in the voltage, which is dictated by over here, but the current has an instantaneous change, which is allowed in a capacitor, but not so in an inductor. So I'm going to use a capacitor to do this. And the way that I would do this is, I just took a look at one because they're all the same. And if I can find the area under the curve, VC of T equals 1 over the area, essentially, of that. And here's my current. So my current would go to 10 milliamps. And the time is 0.5 milliseconds. My voltage is going to slope up to 20 volts. This is my voltage. And because this goes negative, we're all set. So it's going to go ahead and do that. So all I need to do is I just need to find the area under this curve. So VC of T at 0.5 milliseconds. So T equals 0.5 milliseconds. We see equals 20 volts. That has to equal 1 over the capacitor times the area under the curve. How do I solve for the area under the current curve? It's just a rectangle. So it's 20 volts equals 1 over C, length times width. Solve for C. And that's the test. Questions? Nope. Just a capacitor. If you put a resistor in there, you technically could put a resistor, but what makes it more challenging for the resistor, if you put the resistor circuit, is now you actually have to subtract that voltage drop across there as well. So what I'm saying is, if you have a resistor, so let's say we knew we had a capacitor here. Now I have to include that voltage drop here, and then I still would see VC of T. I can get there from here. The resistor actually is going to make it so it's not going to be sharp. It actually is going to do something like this. The resistor is going to slow down the rate of charging or discharging the capacitor, where an ideal capacitor can theoretically do instantaneous changes. It can instantaneously charge and instantaneously discharge. But the resistor is going to say, no, we've got a time constant. Let's slow our roll. All right. We need a little bit of time to talk because most of you, this is your first test you've taken with me. So I just need to get a sense if this is at the right level of challenge. Was it too hard? Was it too easy? Were you fairly well prepared? Do you need more homework? You need less homework? Keep in mind, less homework may mean less, more homework? Is it just the right amount of homework? Okay. Yeah, so what I'm looking for is, because again, it's similar material that I've taught in the past, but I'm teaching it very differently. So I don't know if it's reasonable. I'm looking for, it's called continuous improvement. So because this is new course for me and you all mostly are new to me and vice versa, how do we make sure that you feel like you're learning, or is this at a good pace? Is it too hard? I know that my tests tend to be more challenging than my peers in EET, but hopefully that doesn't mean that it's unfair. It just means that I expect deeper learning, maybe. I don't know if that's the right term. It's not a criticism of anybody. It's more just a different approach. And I'm hoping that this will give you the deeper learning so you'll be able to remember this when you get out and see, like, here are the basics. I tend to do a lot more math because if you can do the math, it really makes understanding this stuff a lot simpler. I don't have to wave my hands and say, here's the result. What do you think? How about anybody in TV land?
Good so far.
Yeah, no, not too hard, not too soft, just right.
Seemed that
3 little
the
bears.
the test was easier than the homework, so I was always looking. I was like, I think I'm under. I assume that there's something else I'm missing in the test questions is where I got caught up.
Okay. Anybody else have thoughts?
Yeah, to me, it was kind of normal.
Kind of normal?
Yeah,
Okay.
I was actually expecting something harder,
Oh,
but yes. So, but as I was going through the questions, and then I realized that was, on my opinion, even simpler than some homeworks that we did.
okay. So Nate and Moise brought up sort of the same comment, which is they felt like the homework was harder.
Yeah, I mean, I was expecting it to be more like, the 422 level of, difficulty level of test. That's why I was expecting it was just like.
Yeah. So there's another student, there's a couple other students who are taking another class with me. And the other class, the first test was a lot more challenging. It was over pretty much all new material for the most part. This one was a review, so it might have been just sort of rehashing stuff. And then going back to the comment about the homework should be harder because you have unlimited time essentially. So if it takes you 10 hours to do homework, then I'm not saying you should, I'm saying if it takes you 10 hours, you only have 2 hours and 50 minutes or so to do a test. I can't challenge you the same way that the homework would because you don't have that sort of unlimited time frame. And I'm not saying you truly have unlimited, but you have a lot more time to do the homework. So the homework is where you're doing the learning. And I would also say the test problems might be easier because you did the homework, because now it makes sense. You did the learning, you did the processing, you figured out, oh, these are the steps that I need to do to go ahead and be successful to understand these concepts and material. Ethan, you said something and I.
This test is definitely challenging, take more than anyone, but
Okay. The key thing is I want to make sure that you all think that it's fair and that there were no surprises, meaning you weren't prepared for any parts of the test, that you were at least exposed to the material and it wasn't unrealistic to say, here's a problem on the test, because this is a chance to say, I've got to spend more time on this, or I got to think differently about the types of problems that I'm doing. Because the next test is going to be almost all new material for most of you all, and it's going to be a lot more math. This one is review and circuits. The next stuff is it's basically like an applied math class. That's the intent that we're going to do anyway. Not to scare anybody, but. Okay. Let's just do a tiny bit, at least motivate you. Okay, so the reason why we have to kind of do a little bit more in-depth math, because all the stuff that we've done to this point has been to sort of look at things, as much as we can in a steady state concept, to look at things in terms of not really considering what's happening with capacitors charging and discharging, inductors charging and discharging, and kind of ignoring some of those things. And unfortunately, we really can't do that to truly get an understanding. And it could be even for systems that are not electrical. If you think about the dynamics of your vehicle, and you can look at your suspension or your strut on your car, and that is an engineered piece of equipment. There's a spring typically associated with it, but there's usually also a damper associated with it. And so how that device responds is it doesn't have a constant spring, because if it's a constant spring, the vehicle would just, you'd see it bouncing down the road essentially, because there's nothing to dampen out the oscillations. There is a little bit, but you'll see cars sometimes going down the road and you'll see a tire just vibrating the whole time. And that's because the damper on that particular wheel is shot. It doesn't work anymore. So there's a couple other things, but that's one of the primary reasons why it's vibrating like that. So the concept that we're talking about here is understanding how do we actually analyze systems that are real world problems that don't have ideal voltage sources, don't have ideal characteristics, have charging and discharging, and it is based on the concept of time. So we're going to have to do a little bit more work to get ourselves up to speed to understanding that. So this is a term that you probably never heard, and it's called complex frequency. That doesn't mean it's called hard frequency. It means that the frequency has a real part and an imaginary part. And the real and the imaginary parts are necessary essentially to go ahead and replicate sine and cosine waves. And we'll talk about that when we get into Euler's or Euler's identity. So we're going to come up with a complex frequency that we can represent every system there is. DC systems, exponential systems, or sinusoidal, sine wave and cosine systems. And so if we have a signal that has this characteristic here, has a magnitude, Vm, then it has an exponential term, and it's usually going to be a decaying exponential. Very few systems don't have a decay exponential, because if they were to increase, then the system would blow up essentially over time. And then it has a cosine waveform. And we only use cosine because actually using cosines makes the math a little bit easier. For those people in my 422 class, we actually do, we do the power triangle and how, not the power triangle, we do the power calculations using cosine waves, because the trig identity for cosines, when you have a doubling there, is much, much easier. So we'll use a cosine, and this is just the generic form of any input waveform, voltage or current. Okay, it's not going to be power, it's not going to be impedance. This is only these are the only power sources that we have in electrical circuits, voltage or current. So you could say the same thing with I of t, some magnitude, e to the gamma cosine of omega t plus theta. The theta is in there because in real world systems, we introduce phase shifts, particularly in AC systems. So the sine waves aren't necessarily going to start at 0, or the cosine waves aren't going to start at 90 degrees. They can be shifted depending on where you are in time. We also have to consider the fact that it might not be DC, so it could be a sine wave. Now there are 3 cases. It's DC when all 3 of these are 0. And I only added in the theta equal to 0 this morning, because when you have DC, you don't have the concept of phase shift. So that's also equal to 0. So my V of t, what that works out to be is just V0. That's my initial condition. It's the magnitude, and it never changes. It's a fixed value. If it's a sinusoidal waveform, so this is purely sinusoidal, then it has a magnitude, and then it has a varying waveform. It's the cosine of omega t. Yes, sir. It's just a variable. It's just, people like to use Greek letters for some reason. So that is, if it's an exponential, it's what power that's raised to. So eventually we'll see how that's proportional to our time constant. If you remember from, well, maybe you're not there quite yet in 312, but you don't cover time constants in 111, I don't think, correct? Oh, you do cover them, RC and RL time constants? Not RL, okay, so you're doing that in 312, okay. So you'll see that this gamma term is equivalent to, or proportional, inversely proportional to our time constant. So this is just a standard sine wave or cosine wave with no exponential term. And most of the time in sinusoidal waveforms, you don't want DC. So our real world power system over here, if you had DC on it, would cause major, major problems. So it's very rare that you want DC and AC combined, except for sometimes maybe amplifications and amplifiers, where you want to go ahead and set the center point, like a class AB amplifier. You set the center point in the middle and it can go up or down on the sine wave to go what you need to. To get a sine wave, everybody thinks this has to be at 0 volts. Doesn't need to be. I can make a sine wave out of a DC source. May not be a good looking one, but I can go ahead, whoops. Get this out of the way. I can go ahead and I can turn on a switch. Here's my load. And I can turn that switch on and then turn this switch on. And I can get positive current going this direction. But I also can have another switch that I can go ahead and flip-flop that. And like this. So at this point now, this is plus to minus when this is positive. And then when this is going through, it swaps that direction. So there's no 0 volts here, right? It's a DC source. But how do you make a sine wave out of a DC source? You don't really change the ground reference. You just literally swap the leads, how your load is connected. So if you talk about an H bridge, that's essentially what an H bridge does. It's just constantly swapping leads back and forth. Okay. And even in real world power systems, when we have a generator, the only time I have a generator, and I'll show you a very simple one, we'll assume it's 3-phase. That's a real world generator. That's how it comes connected. Sometimes Y, usually Y, but it doesn't have any reference until you connect its reference point to ground. Then you provide a reference. So a sine wave doesn't necessarily need to be referenced to ground. It usually is because we want to take the DC out of it. But all we say is that there's no DC so that the positive peaks are the same as the negative peaks. That's a pure sine wave. And then if it's an exponentially either increasing or decaying waveform, we have it could be the DC value that we have, but we're either increasing it or decreasing that exponentially. And an exponential is in accordance with time. Let's see if I want to do this. Oh, so this will be the last slide. So what we're going to do is we're going to come up with just a general expression that we're going to be able to combine our complex exponential, that e to the alpha t, or gamma t, I should say, and our cosine of omega t plus theta. We're going to be able to combine those all in one fell swoop. And there's going to be a little bit of math to get there. But what we're going to see is we can make this value k is essentially going to be our magnitude term. And then our e to the st is going to include a real part and an imaginary part. Okay. So the s term usually is written as s is equal to this gamma plus our j omega. That's how we make it complex, because we want to combine the decaying exponential part with the cosine part. And we'll see how to combine those two in the next class. That's all I had. Well, that's all. I have lots more, but I don't want to burn anybody out. It's awfully quiet, so that's usually a sign people have had enough. Any questions? Still there?
Yep.
Yep.
Okay, so for those of you who took the test live with me and you want to come get your tests, either, see me during office hours. I'm in and out all day today. I've got a bunch of meetings. But you can try to connect with me today, or you can just come in class. I'll keep them for a little while. If you want to check your grades or check how you did. Your grades should be all in Brightspace. All right, folks. That's all I had. Have a great weekend. Thank you.
Thanks, you too,
Yeah.
Paul.